Hello guys, welcome to video lectures of DSD classes. In this video lecture, I am going to explain about third unit basic concepts and what are the logic gates we are using in combinational circuits. So in third unit we have combinational circuits, logic gates, how we can analyze combinational circuit and logic function formation between input and output, Boolean algebra, gate level minimization, combinational circuit implementation and truth table based implementation, implementing combinational circuit design and different combinational circuits like adders, subtractors, encoders. In this video lecture, I will explain what is digital circuit and logic gates. So digital circuits are mainly a circuit which will consist of digits, right? Digital circuits or digital electronics is a branch of electronics which deals with digital signals to perform the various tasks to meet various requirements. So digital circuits are mainly based on the digits like zeros and ones. So the input signal applied to these circuits is of digital form, so which is represented in ones and zeros, a binary language format. So mainly these are designed to overcome the disadvantage of analog systems, so which are slower and the output data which is obtained may contain an error. So mainly digital circuits are implemented or designed by using logic gates. So these are AND, OR, NOT, NAND, NOR, XOR, XNOR are the basic logic gates. So we have digital circuit mainly divided into two types. So one is combinational circuit, second one is sequential circuit. So first of all, we have to know the difference between digital circuits. So differences of these two we have to know: combinational logic and sequential logic. So in combinational circuit, output depends only on its input at that time. So whatever the input given, based on this present input, we will get the output. So coming to next circuits are sequential circuits. So these are also digital circuit. Unlike combinational circuits, so here the output depends upon present state and past histories of the output also. So means here output depends both on its previous output and its input. So these are some of the differences between combinational circuit and sequential circuit. As we discussed right now, combinational circuit output depends upon only present input, whereas in sequential circuit output depends upon present input and past outputs. So the feedback path is not present in the combinational circuit. So because here output depends upon only present state, so there is no feedback form. So whereas in sequential circuit, feedback path is present because output depends upon previous history. So whatever the previous history, that history is used as the input. So here in sequential circuit, feedback path is present. So in combinational circuit, memory elements are not required because we no need to store any element. So in combinational circuit, there is no memory element, whereas in sequential circuit, there is a memory element. Memory element is present in sequential circuit. And one more important the difference between sequential and combinational circuits are, so in the combinational circuit, the clock signal is not required. Okay, so whereas in sequential circuit, the clock signal is required for sequential circuits. So then the combinational circuit is very simple because output depends upon only input. So the design is very simple. So whereas sequential circuit, unlike combinational circuit, sequential circuit design is very complex. Okay, so these are some of the examples of combinational circuit. So every digital circuit's basic building block is logic gate and adders, multiplexers, decoders, encoders. These are some of the examples of combinational circuit. And for sequential circuit, examples are latches, flip-flops, counter, registers. So these are the main six differences between combinational circuit and sequential circuit. So then what is the logic gates? So logic gates are very important in every digital electronic circuit. So without logic gate, there is no digital circuit, right? So digital electronic circuit operate with voltages of two logic levels, namely logic 0, which is known as 0 volts, and logic high, which is logic 1. So the range of voltages corresponding to logic low is represented with 0. Similarly, the range of voltages corresponding to logic high is represented with 1. Right? So logic 0 is 0 and logic 1 is 1. The basic digital electronic circuit that has one or more inputs and single output is known as logic gates. Right? So for a logic gate except NOT gate, for remaining all gates we have more than one input. So for AND gate, OR gate, NAND gate, NOR gate, XOR gate and XNOR gate, we have more than one input and output is only one output. So basically these logic gates are divided into three categories. So first category is basic gates, so which are NOT gate, AND gate, OR gate, and second one is universal gates. So those are very important gates. So why these gates are called as universal gate means, so using universal gates means we can, using only NAND gate, we can implement remaining logic gates, and any Boolean function or Boolean equation can be implemented by using only NAND or using only NOR without using NOT and OR. So universal gates or NAND and NOR gates are called as universal gate. This is very important topic. So next, third specialization is nothing but special gates. So special gates are XOR gate and XNOR gates. So these are the three categories in logic gates: basic gates, universal gates and special gates. Let us discuss about logic gates. So these are the logic symbols for each and every gate. So first one is AND. This is the symbol of AND. So output is logic 1 when all the inputs are 1. So then only logic gates are called as so coming to first gate, AND gate. So this is the logic symbol of AND gate. Output is at logic 1 when and only when all inputs are at logic 1. Otherwise the output is 0. So this is the Boolean expression x equal to a dot b. So next gate is OR gate. So this is the logic symbol of OR gate. Output is logic 1 when any one of the input is 1. So output is 0 when all the inputs are 0. So output equation for AND gate is x equal to a and x equal to a plus b. So this is plus symbol. Or if any one of the input is 1, then output is 1. The next gate is nothing but the NAND gate. So this is the logic symbol of NAND. So NAND can be known as AND followed by NOT. So whatever the AND gate description, it is complemented to the AND gate. So output of AND gate is 1 when any one input is 0. Means if all inputs are 1, then only output is 0. In remaining condition, output is 1. So this is the logic Boolean expression x equal to a dot b bar. So a dot b complement. So complement of the AND gate is nothing but NAND gate. Complement of OR gate is nothing but NOR gate. So these two are nothing but the XOR, XNOR and NOT. NOT is the complement of the AND gates. So NOT is the complement of any input. So if a equal to 0, then complement of 0 is nothing but 1. That is the complement of AND gate. So next is nothing but the truth tables of all logic gates. So these are the truth tables of all logic gates. So, buffer gate. So buffer gate, if whatever the input, that is the output. So second is nothing but NOT gate. NOT gate is complement of the input. If input is 0, output is 1. Input is 1, then output is 0. AND gate. So AND gate output is logic 1 when all the inputs are at logic 1. So next is NAND. NAND is the complement of AND. So if all inputs are 1, then only output is 0. In remaining condition, output is 1. OR gate. OR gate is nothing but if any input is 1, then output is 1 for OR gate. So OR gate's output is logic 0 when all the inputs are logic 0. So next is NOR. NOR is complement of OR. So output is 1 when both the inputs are 0. In remaining all condition, output is 0. So next XOR gate. XOR gate's output is 1 when inputs are different. Means when A is 0, B is 1, then output is 1. Or A is 1, B is 0, then output is 1. Whenever both the inputs are same, then output is 0. Means 0, 0, output is 0, or inputs are 1, 1, then also output is 0. So this is the logic symbol, output equation. Y equal to A XOR. This symbol, we have to call this symbol as XOR. So Y equal to A XOR B. So output equation is A bar B plus A B bar. That is the output equation for XOR gate. So next is XNOR gate. XNOR gate is complement of XOR gate. So when both the inputs are same, then output is 1. When both inputs are different, then output is 0. Then this is the Boolean expression Y equal to A XOR B complement. So A bar B plus A bar B bar plus AB is the output equation for XOR gates. So any digital electronics or digital circuits, basic building blocks, without logic gates, there is no digital circuits. Okay, so logic gates are the basic building blocks of digital circuit. So these are the different digital circuits we have. So we will check what is the VHDL codes for these gates. So these are the different VHDL codes for this is first one is for NOT gate. So for NOT gate we have only one input. So first one is library declaration. Next one is use package declaration IEEE.std _ logic _ 1164.all. This is nothing but the package declaration, and this is library declaration and entity and architecture. So in entity name is, so here the entity name is NOT gate, and port X only one input in STD logic and Y out STD logic. STD logic is a signal type which will have only one value. So either 0 or 1. So next is nothing but the architecture. So architecture name of entity name is begin Y gets not X. So here Y is the complement of X and end architecture name. So whatever the architecture name, here architecture name is data flow model. So that is the architecture name. So this is an VHDL code for NOT gate. So coming to next gate is nothing but AND gate. So except NOT gate, remaining all gates we have more than one input. So for example here I take two inputs as input and Z as output. So a port X is in bit or in STD logic, Y in STD logic, Z is out bit. So any port is nothing but a declaration of inputs and outputs. So we can define inputs. So port, the syntax of an entity is entity name is port, signal name, mode, signal type. Here X is mode in and Y is mode in and Z is mode out. And the architecture is nothing but begin Z gets X and Y. So Z is AND between X and Y. Okay. So this is the VHDL code for R, same as AND. So here also we have two inputs X and Y and only one output Z, and Z equal to X or Y. So these are the three basic gates VHDL codes. And coming to this special gate XOR gate. So whatever the gate, if it is NAND gate, NOR gate, XOR gate or XNOR gate, so we have to replace this AND keyword with that gate. So if we want to write a VHDL code for NAND, we have to replace AND with NAND. So if we want to write a code for NOR gate, we have to replace AND with NOR. So this is an example for XOR gate, how we can write XOR gate. So these are the different VHDL codes for logic gates. So once again I am repeating, we have different types of logic gates and OR, XOR, XNOR. So using this we can design combinational circuit analysis. I will explain that combinational circuit analysis in the next lecture. Thank you so much for watching.